Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Right, thank you very much. My name is Hayduk Noushadi. I'm a member of UCLA's Embedded and Reconfigurable Systems Lab. My advisor is Professor Majid Sarafzadeh, and we are a member of UCLA Wireless Health Institute. In this talk, I will go briefly over the Wireless Health Institute and what is the mission of that institute, and I will present one of the projects that we are pursuing actively in this institute, and it's regarding the detecting human imbalance in real time outside of the laboratory environment. So the whole idea of wireless health is to leverage the wireless technology and microprocessor technology with medical science to extend the healthcare outside of the hospital and clinics. So in order to, by achieving that, we can deliver the personalized healthcare to each individual, such that the solution is adapted to an individual, and that will make them capable of being monitored continuously and globally outside of the laboratory environment, as long as there is a connectivity. So Wireless Health Institute at UCLA, it's a campus-wide collaboration, and it has support between industry and community partners. So the whole vision behind wireless health is that in the future, we have our homes as a pervasive environment that all systems that currently we are using will have some sort of wireless connectivity, and we will have this body area network on the human that somehow they can talk to those devices around them. And using cellular and wireless network, the collected data will get transformed to a medical enterprise or a clinic. So there will be designated people who can monitor patients outside of the hospital. And also, there is a chance of emerging this new model of business, which we call them call center services. So, for example, I can register myself to one of those call center services that they can monitor some of my vital signs or any health data that I'm interested in. Or if they see any irregularity, they can notify the patient or any caregiver. So Wireless Health Institute at UCLA, it's a big camp. I mean, it has a collaborator between different schools of medicine, UCLA Medical Center, School of Engineering, School of Nursing, Public Health Department, Anderson School of Management, and also College of Letters and Science. What we focus on is not just building a device to address building a mobile devices to address healthcare, but it's more like end-to-end solution that we talk with the physicians in medical community. We see what's their need, or they bring us their need, and we try to solve their particular problem and aggregate that data and make them accessible for them. So, and also developing new tools to analyze that data and helping them to come up with better diagnosis and extend the whole notion of healthcare outside of the hospital. So now I will talk to a smart tool that we developed, and the main goal is to prevent falls. Why do we stress on falls? Because, as we know, instability is a major cause of morbidity in the elders. This is according to Center of Disease Controls. So falling is the second cause of accidental death in the United States. The whole idea is that, according to geriatric experts, there are some precursors to fall that if at the exact time we can detect them, we can let the caregivers of those elderly know that some parameter shows that the patient has higher risk of falling. So maybe they can then be more careful about them. For example, if my parents, one of them, been identified with high risk of falling, maybe I won't let them to go to grocery shop by themselves. I will be more watchful. So 75% of all victims of fall are elderly people. And usually the falls are responsible for 70% of accidental death in the person 75 years and older. And as you can see in the graph, the older a person is, the rate of the rate of mortality due to falls is increasing dramatically. Also, 5% of all hospitalization in the US and 40% of nursing home admissions, nursing home admission rates are related to the people or patients that have been falling. So, in addition to that moral dilemma, also there is highly huge cost associated with falling. So, the hospitalization after fall cost our healthcare system $25,000 to $75,000 per case. And the cost of imbalance related to fall in the United States has been estimated to be about $20 billion. And this is for year 2006. And by 2020, the cost will increase by approximately $32 billion a year, which is a huge amount of money. And also this graph shows that for people above 65 years, older than 65 years old, each fall, with the statistics that they gather from 100,000 people, 40 to 80,000 of those fatalities were due to fall. So this shows that the elderly people are really susceptible to fall. So how we can basically somehow mitigate that? So we try to bring balance everywhere. This is the whole idea of having a smart shoe which has a sensing and electronic devices in it, plus a software that can extract the parameters that are important precursor to fall, according to geriatric experts. It's a portable and affordable device. And also it can be multi-purpose. Doctors can use it, elderly people can use it. And also it can be used in different aspects of our social life, like running. Doctors can use it to monitor the patient's data. So elderly people can use it to somehow, if they are not monitored by physicians, their caregivers or their close relatives can know about their health condition. And also, we have tested it with our athletes at UCLA. So runners can use this system to somehow get the proper regime of running based on what their trainers are asking them to do. So we measure imbalance using a variety of techniques. The whole idea is to insight into the user's daily walking pattern. So it's very important to note that since this is just a regular shoe, I have a pair of it with me. After the talk, I will just pass it around. You guys can see. So it's a normal shoe. And there is nothing heavy associated with it. And as long as I have a cell phone device, I can use this shoe. And that software can run on the cell phone. And it can extract all the data necessary for me at the end of the day. And since it's wearable and it's not tied to a laboratory environment, we can use it consistently. So one of the issues that we had with laboratory solutions to address imbalance is it's very heavily biased toward the laboratory environment. The fact that the patient can walk straight in a room doesn't mean that he will have the same balance parameters when they are walking outside in the street due to different physical and environmental factors. So I will here explain some of the techniques that currently is used by physicians and geriatric experts to assess human balance. So one of them is gait lab, that usually elderly people will go there once in a while and they will walk, and physicians will look at how some of their gait parameters, and based on that they will come up with either they have a poor balance or a good balance. There are motion capture systems that are very expensive cameras that are again assembled in gait labs that geriatric experts are using for balance analysis. And there is this system called PEDAR, which is an install with 100 sensors in it, which is costly. The cost of PEDAR is almost $25,000 to $30,000, just the install and Bluetooth module. Even though it's mobile, but it's not affordable for many people to use it outside of the lab environment. And also, there are some cheap methods of assessing human balance, which one of them is just observational, physicians are asking the patients to walk up, walk 5 steps, turn around, walk back, and sit down, and they're visually trying to inspect how the balance is changing. So our proposed system is trying to take advantage of different data modeling techniques to shift the accuracy and basically influence the capability of our mobile platform to detect what this more expensive system are able to do. So this is the whole architecture. You can see here the first prototype that we built for our shoe. So I have with me the second one, and we are in process of building the third one. So it's just, our shoe has, in the insole, we have these pressure sensors. It's point-based pressure. So we make some study and we find what are the most effective places that we can place those sensors. And these are adjustable because the location is very dependent on each person's walking behavior. That means there should be a calibration phase that they can walk. And based on that, we can adjust where those sensors should be placed. So we have the processing unit, which is in the first version was a Berkeley micromode. In the second version is a microlip. It's a new technology built at UCLA's electrical engineering department. So the micromodes, they have radio module. We also put a Bluetooth interface on top of the radio module. And we attach a 3-axis gyro and 3-axis accelerometer. So we use gyro and accelerometer for some basically for detecting some of the gait parameters that are dealing with the distance. So, and also pressure sensor to detect the harmony, the way people are walking. And you can see that there is this software that can run in mobile device, and it can be adjusted. The sensitivity of it can be adjusted, and there's a calibration phase that it tries to set the thresholds and parameters for each individual user. And it can, after a while, it can report a fall risk. And we have 3 levels of fall risk. The green is normal, the orange is moderate, it's not that bad, but the red is really severe fall risk. So here you can see the monitoring software of this. We just built this for demonstration purposes, but the algorithm which is running behind the scene is the same which is running on the cell phone device. Well, when I demo, I will demonstrate this. Then you can see that when I perform a walk which will have higher variability of balance parameters change, the color of the screen will change. And eventually the system can notify a caregiver. For example, the data that will get transferred to a call center, they can set up an SMS or an email address, and immediate message can send to the caregiver regarding some cases that system has been detected. So here I will show some of the results that we got from SHU. We basically look at 2 spatial and temporal parameters of the human gait. So, and what we look at is the variability, because according to expert, what is important is the variability, not the actual value. So if I have a consistent walk with not so much variation of those gait parameters, that means that I, as a person, have a normal balance. So the balance is abnormal when there is higher variability. So in the this graph shows there are 3 types of, based on, we did our experiments, and here you can see 3 types of walk. The first one is constant speed walk, which is very harmonic walk. The second one is a variable speed walk, and the third one is an inconsistent walk. So as you can see, the parameters that we changed, the variability of the first walk is almost, the first walk has less variability than the second walk, which is inconsistent. When we come to more inconsistent one, we can see the higher variability in stand time. Stand time is one of the gait parameters that we extract from user. And there is another important thing that we look at it's the trend line, because the fact that a person can walk fast and then can gradually slow down their walk, that might show a higher variability in some of their parameters. But when we take out the trend line, so the variability will level up. Because if I start walking faster and I'm with the constant speed, I decrease my walk. If I take into account the trend, then the parameters will show that I have a normal balance, as you can see here for 3 walks. Once we take out the trend, you will see that the inconsistent walk will have much, much higher variability than consistent walk. So we also are able to assess the risk factor. So I'm not going to go to more detail on the algorithmic side of how we do that. I will be more than happy to answer any questions further if you will have. But once we will have different class of risks, and for each of those class of risks, we will find the basically variability range of all of those spatial and temporal parameters, and based on that, we will assign the risk value. And here you can see that, for example, in the second graph, is the risk distribution that we find in each of those same type of activities on human walk. And you can see that, for example, this blue one is a constant walk, while the green line is variable speed walk. So you can see that some part of the distribution is overlapping, because in the variable speed walk, we have a section which was matching with the constant speed walk. But when we go to much more irregular walk, the risk distribution is shifting more to the right side, which means that the person would have the higher risk of falling. Okay, so now I would like to demo how it works. So the idea is that they will take the shoe outside of the lab environment and they will walk. The main idea is to collect the data for a longer time, for a large amount of time, maybe a day or 2 days or a week. I increase the sensitivity of the system so high, so here I can demonstrate in the short walk, because I cannot walk for so long time, that how it will behave in the real case. So, this is not good. So, yeah, unfortunately, I don't know how to fit this in the screen, but okay, I will show part by time. In one time in right side, you will see these are the accelerometer data that we collect to perform some of our calculations, and you can see in the middle side you can enter the patient's information, and in the right side there are pressure associated with each of foot, like I'm in my left foot or I'm in my right foot. We use that to detect harmony. So when the background of the screen is white, that means there is no movement. When I start walking normally, it should go to green, and gradually if I start demonstrating irregular walk, it will go to yellow and eventually red. So I'll try to. So I'll walk. So that color change is normal because I got some imbalance naturally. That's due to human natural imbalance. So now I will try to demonstrate limping. Normal walking, then limping, which in order to change the variability of my walk. You can see it goes to red and come back to green. And I will try to show some, like when drunk people, they really lose their balance. They go left and right. So then you will be able to see that this is smart enough to pick it up. Okay. All right. That's for my talk. I'll be happy to answer any questions. Yes.
This is really cool work. I was curious to know where you guys do the processing. Is it done on the phone or is it sent to some server?
So we have stage processing. For example, some of the processing is getting done on the mode, like filtering, some preliminary filtering. Then there are some processing which is happening on the phone. So, and you can adjust which amount of processing you want to shift to server or you want to keep on the phone, depending on how critical the situation of the patient is.
Okay, I guess I was curious to see if you can use the output of the phone processing to call someone.
Yeah, actually, yeah. Actually, I think your phone number was here.
Actually, when it got red, I got a page.
Oh, okay. That's cool.
Yeah.
And you can read the page. Let's read it for everybody.
Oh, for everyone? Okay. So, Nashadi poses a fall risk. Please contact the patient.
So it's my last name.
Or he's drunk.
Or I'm drunk.
You say this is the way to check your students are drunk?
Yes.
That's excellent talk, really.
Thank you.
Given that one of the biggest factors in deploying health-preserving technologies amongst the elderly is acceptability.
Right.
For example, trials of hip protectors, it was very hard to get elderly people to wear the coal buttons around
Right.
you can wear around your neck.
Right.
A lot of elderly people simply will not wear them. Small devices that are unobtrusive make up a very crude signal. For example, the Nike Plus device
Right.
in the training suit, which could get over some of the issues of acceptability of wearing an obvious device. Have you done any trials or thought of doing any trials that compare a very crude signal, for example, from the Nike Plus device that's being produced at low cost by the manufacturers, not passed on to the customers, but could be deployed in large quantities, and also combination signals, changes in body temperature and heart rate are often antecedents for along with gait. So if you could capture from a wristwatch change in body temperature, heart rate, and a very crude signal from movement, it may be
Yeah.
accurate with determining a fullness of activity.
Sure. As far as your second comment, we are in talk with the experts outside of the geriatric department because, as you mentioned, we recently find that there are other parameters that might have an effect on human balance, not only except the gait parameters. So for us, we need to talk to them to get the literature to know what's going on. We are in process of that. I just find it maybe 3 days ago that there is a possibility, and we are definitely doing that. And I wasn't clear regarding your first question. You want to know, have we done any clinical studies with this shoe, or? I wasn't clear.
Sports medicine studies at the moment.
Right.
But I haven't seen any in this more important area of potentially detecting signals around changing gait. The signal would be very crude from the Nike Plus device. I was just wondering if you investigated what utility you would get from that.
At this moment, I don't have answer for that.
I can make a
Yes.
response. So you get pretty much nothing from Nike device. And this being non-intrusive is very important. So if you actually maybe later look at the shoe of someone who is very deaf, need not to know this is a different shoe. Even at this prototype stage. We are currently manufacturing 20 of them in our lab. And this manufacturer version, you will definitely not be able to tell if it's a different shoe. So very important issue. Elderly or young people don't want to know they're wearing something. We also have a cane. That's different, actually. They told us to make it look like it's different because it has a bad stigma, traditional cane. Whereas we make it cool and high-tech, people will actually wear it. So we are really talking to people who are involved with UI and guidance and coaching to learn things of this type. Very good point, so.
Yes,
A couple more questions. We've got time, so if that's okay.
please.
I have, my question concerns the actual calibration in terms of, we're changing colors and saying the risk of fall.
Uh-huh.
Have you actually had, how do you calibrate that? How do you actually know that this is the correct, this is really does, when it turns red, we get a page, is it then the false hit or what?
No, at the beginning, so this was calibrated on my walk, but at the beginning there is a phase that we will ask patient to walk. So when they walk, there is a base case, because if there is a person who is limping regularly, detecting limp as a fall risk might not be accurate. So we will detect all those parameters during that calibration phase. And that will be the base rule to see, because we are looking at variability of the signal. So
And I assume you don't have enough shoes and test cases to actually have figured out.
we had 4 of them, and we gave it to UCLA's VA hospital. They did some initial testing, but as my advisor mentioned, we have in process of building 20-25 of them, so we can go for a clinical trial.
So these algorithms for detection of fault is not something we cook up. Geriatric doctors have a manual which says this is a normal law, this is not, and those we can accurately measure. In fact, with 97% accuracy, compared to those systems that Hajduk showed, which cost typically around $250,000. This is a $200 shoe.
Yes.
I also enjoy your talk very
Thank you.
much. My question related to when you apply the smart shoe to a runner.
Okay.
When you're running, obviously the biomechanic of your foot is very important.
Right.
How does the software, when analyzes the fall risk, considers if you are an overpronator or supinator?
So maybe I put it wrong. Obviously, the software will be different. When I say it can be used for runners, I mean just the shoe as a hardware platform.
Okay.
So that hardware platform, obviously, for the running purpose, needs to have a different software to interpret data for the way that is suitable for that particular application. What we had in our mind when we were designing this shoe is having the shoe to be used not only for balance, but being as a computational platform that other people can use for different purposes.
So you can actually take this from us and put your own software for ulcers, foot ulcers, for children, learning to walk, you name it. Okay. This is really a platform. And imbalance is one example that we learned all the way, and currently we are designing a clinical studies for.
Thank you. I don't know if you have time to
Yeah, well, I'm transitioning.
Sure.
If it doesn't, John has mine.
What kind of? So the first version was Mica 2.
Okay.
The second version is MicroLeap.
Okay.
That was designed at UCLA.